Alright, in this video we're going to go backwards. In previous videos you've been given some sort of a function and you're being asked to graph it. But in this video I'm giving you the graph and I'm asking you to write a function to go with it. Later in the video we're going to talk about discontinuities, and you're going to sketch a graph that has a removable discontinuity, a non-removable discontinuity, and one that has both. Alright, so we'll talk about what the different types of discontinuities are. Alright, for number 11, let's go ahead and build a function that matches this graph. So I'll call it f of x equals, let's start with the vertical asymptote because that's the easiest. We have a vertical asymptote here at -3. The denominator, if the denominator is x plus 3, that would give me a vertical asymptote of x equals -3 because of the way we would set it equal to 0 and solve. So I'm liking my x plus 3 denominator, which would give me a vertical asymptote at -3. So that's great. So now I need to have a horizontal asymptote at 2. There's two ways I can accomplish that. When the degrees are the same, the horizontal asymptote is found using the leading coefficients. So one thing I can do is make sure that the degrees are the same in the numerator and the denominator. So far I have a denominator that has degree 1. So I can just make sure that the numerator is degree 1 also by making it x, or like x plus 1 or whatever. This number right here doesn't matter. Alright, you can make it anything or nothing at all. The key is to make this have the same degree. So now that these are both the same degree, the horizontal asymptote will be determined by the leading coefficients. Right now the leading coefficients are 1 and 1. So at this moment I would have a horizontal asymptote of y equals 1. Alright, that would be too low. I want it to be 2. So I can change that if I make the coefficient up here be 2. Okay, and now that would be 2 over 1, which would give me a horizontal asymptote of y equals 2. So there you go. This is one solution to the problem. Okay, a horizontal asymptote of 2 and a vertical asymptote of -3 from that. But there is another solution to the problem. So another way you could approach it, maybe I'll just say or. Either way, I'm going to do the x plus 3 in the denominator to get that vertical asymptote. But another way I could get a horizontal asymptote at 2 is by making the top degree less than 1. So in other words, I need the top degree to be 0. That means this would be a constant. So I could put any number up here. I could put a 1 up here, or I could put a 5 or a 13, anything. I thought I was erasing, but I wasn't. So I'm going to put a 5. Alright, but the point is this is degree 0. Alright, and this is degree 1. So the top degree is less. And we've learned that when the top degree is less, when the numerator degree is less than the denominator, then the horizontal asymptote is y equals 0. So right now the horizontal asymptote is right here at the x-axis. So that's too low. I want it to be up to more than that. But rather than changing the degree like we did before and changing the leading coefficient, what I can do is simply add 2 onto the end. That would shift the entire graph up 2 and give me the same result of having a horizontal asymptote at 2. Okay, so this is another solution to the problem. Alright, just for fun, I'd like to take a peek at Desmos.com and see if our graphs look like this. Sort of cheating, I guess, a little bit. So I'm going to desmos.com. I should probably have done this off camera. Okay, so here I am at Desmos. My first function is 2x over x plus 3. So I'm going to type y equals, you can't really see this, maybe I'll scoot over so you can. I'm typing in over here, y equals, if I hit the division key, I go into fraction mode, and we wanted, what, 2x over x plus 3. Okay, now this function has the correct vertical asymptote and horizontal asymptote. You know, it has a branch up here instead and down here, but that's fine. We just wanted it to have the right vertical and horizontal asymptote. So notice that it does have a vertical asymptote. I'm going to zoom out a little bit so you can see a little better. It does have a vertical asymptote at -3. Okay, and you can see that even more clearly if I put x equals -3 in there, and that draws the vertical asymptote. And for the horizontal asymptote, we wanted it to be at 2. So if I put y equals 2, and there's my horizontal asymptote. Alright, so I did achieve what I wanted to achieve. I'm a little OCD, so I want these to be dotted lines, and I want them to be the same color. But that's just me. Okay, now I want to check my other graph, the 5 over x plus 3 with a plus 2 on the end of it. Alright, so I'm going to change this to 5 over x plus 3. Okay. With a plus 2 on the end of it. So there you see, now interestingly, this one actually does match with the branches in the correct position to match the graph we had. So, but both of them have the correct horizontal and vertical asymptotes. So it's all good. So that's number 11. Now, let's talk about number 12 and talk about discontinuity and the types of discontinuity. Alright, here's what we learned about continuity. A function is continuous if you can trace the entire graph without lifting your pencil. Another way of saying it is the function is continuous if it's unbroken. So all of these graphs are discontinuous because each of these graphs is broken in some way. Here's an example of a continuous graph. If I had a graph that just went like something like this. Alright, this is continuous. Not because I put arrows on the end. That has nothing to do with it. If I had it begin and end at a point. Alright, this graph is still continuous. It's unbroken all along its entire domain. If I took the same graph and put a break in it, okay, if I took the function and I went like this to it, okay, and I'm considering this to be one function, then okay, it's not cooperating with me. But this is now discontinuous because it has a break in it. So there are lots of different ways to have a break. Now, when you have a break in a graph, it's not called a break, it's called a discontinuity. Okay, so a graph that is discontinuous is going to have some sort of a break in it, but that break is called a discontinuity. So these are the different kinds that we learned about. If there's an asymptote as your break, as your discontinuity, that's called an infinite discontinuity. Alright, so any asymptote is going to be an infinite discontinuity. If you have a gap like this, like a space, that's called a jump discontinuity. Now, if you have a single point that's missing, which we often refer to as a hole in the graph, then that is called a point discontinuity. Now, you see these words here also. The asymptote and the gap, the infinite, discontinuity, and the jump, these are both called non-removable. The whole, or the point discontinuity, is called removable. Okay? And one way to think about removable discontinuity is the fact that you get a hole in a graph when you're dealing with a function and you have a factor that cancels out. So, if I had x plus 2 times x minus 3, and then I had, say, x plus 5 over x minus 3, let's say my function factored down to this. Normally, we would look at the denominator and say, oh, look, I have 2 vertical asymptotes. But we will not have a vertical asymptote from this. This cancels out. Okay, and this is where the whole comes in. Instead of having a vertical asymptote at positive 3, by the way, because we set it equal to 0 and solve, we have a whole at positive 3 comma something. All right, we have a whole. We have a point discontinuity. So notice that we have a whole when you can cancel these factors out. So by canceling these factors out and going like this, we are removing the discontinuity. So now we could go ahead and graph the function using what's left over, and that would show us what the function is going to look like. I mean, it wouldn't look like this. But this remaining part of the function will show us what the function is going to look like, and we just need to make sure we put an open circle wherever the hole is. But because we can cancel out the factor and take the discontinuity away, we call it a removable discontinuity. So that's a lot of extra information, but just remember that when it comes to non-removable and removable, the only removable discontinuity is a point discontinuity when you have a hole in the graph. Okay, so an asymptote is infinite, a gap is a jump, and a hole is a point. And the only one that's removable is the hole, or point discontinuity. That's what you need to know. Okay, so this is an example of a continuous graph, right? Has no breaks in it. This is discontinuous. You see that there's an asymptote here, okay? So this is an infinite discontinuity. That would be non-removable. Looking at this graph right here, you see there's a hole in the graph, so this would be a point discontinuity. That is removable. And see this gap right here, this would be an example of a jump discontinuity, and this is also non-removable. So we've got those examples. So armed with those examples, getting back to the question, now it's your turn to make your own sketch. So we're supposed to sketch a graph that has the following types of discontinuity. Okay, so I'm not going to bother drawing x and y axes. So a removable discontinuity, automatically as soon as you see removable, you should be thinking, okay, that's going to be a point or a hole. Okay, when you see non-removable, that's either going to be an asymptote or a jump. Okay, like a gap. And then of course over here it's the same thing. Removable, that means we need a point. Okay, which we call a hole, or non-removable, where you're talking about having an asymptote. Well, let me use the vocabulary. That's your infinite, which would be like an asymptote. Okay, so anyway, I'm just trying to reinforce the vocabulary. So sketch a graph that has a removable discontinuity. So that just means sketch a graph that has a hole in it. Okay, I mean, so there's any number of ones I could draw, but as long as it has a hole in it. So you know, so I could, here's one. Okay, boom, there's a hole in it. There you go. Anything at all. Okay, I could just draw a straight line. Okay, anything that has a hole in it like that, that's going to be my removable discontinuity. Okay, sky's the limit. Okay, now draw one that has a non-removable discontinuity. So that's either an asymptote or a jump. So I could just draw anything that has an asymptote. So I could draw so here's an asymptote right here. Here's another asymptote. Okay, so if I drew one of our classic graphs like this, it has a nice asymptote to it. So this would be a good example of a non-removable discontinuity. You know, I also could have done a graph that was like this. Okay, that had a gap in it. All right, that's another way to do it. So I'm just going to leave that for now. So removable discontinuity, something with a hole in it. Non-removable, either draw an asymptote or draw something with a gap in it. Now, if I want to draw something that has both a removable and a non-removable, I need it to have a hole in it and an asymptote or a gap. But you know, we've been working with asymptotes a lot, so that's what I'm going to draw. So so here I go. I'm just going to combine these two pictures into one. I'm going to draw an asymptote graph for my non-removable, but then I'm going to put a hole in it as well. So that would be like this. So here comes my asymptote situation. Okay, but when I draw the graph, I'll just put a nice little hole in it. Okay, so there you go. It has a non-removable, which would be my asymptote, but it also has a removable because I put a hole in it.